Hi everyone, my friend in the previous video discussed about functions, and in this video we'll be talking about recursion. So it's just as it means in the English dictionary, recursive action. So in C language, when a function calls itself multiple amount of times inside a function, it is called a recursive function. So this can happen as many number of times as it wants, but it usually doesn't apply to all sorts of problems. The most common ones are in sorting and searching and also in traversal problems. So in our portion we have four main recursion problems. The first is factorial. So we know this concept already in the first chapter because we've done problems related to this, but in this program we'll be using functions and also the recursion. So let's execute this. So as you can see, this is the factorial program. So in this, you can see that the first statement is the function declaration. Then in the main function, the function is being called. Then the function is being defined, where the statements are inputted and the logic is applied as to how to execute and obtain the factorial. So let's take 5 as an example. And in that case, let's input 5 as the number. Then it goes directly to the function definition. So it checks if n is equals to 0, that is not true. Is n equal to 1, that's also not true. So then it executes this return value, where n is 5, so 5 into the factorial of 4. So this repeats again and again till the function is where the n value is 1 or 0. And then this final value is executed in this printf statement. So let's execute this program. Let's take another number. Let's take 6. And the factorial of 6 is 720. The second program is GCD, also known as Greatest Common Divisor. So this is most commonly known as highest common factor that we learned as children, and in this program we will use functions and recursion properties. So let's execute this. So as you can see, this is the GCD program. In this is the function declaration. The function is being called inside a printf statement here, and this is a function definition. So in this function definition, the number first it checks if the second number is equal or is not equal to 0. So if it's not equal to, then it executes this return statement where the function is again being called. So it executes HCF of n2 comma n1 modulus n2. So that's the remainder of n1 and n2 when divided. So this again repeats and goes to the function definition, and it's continued till n2 is equals to 0. So let's execute this. So let's enter two positive numbers. Let's say 4 and 16. So the GCD of 4 and 16 is 4. The third program is called Fibonacci series. It's also a concept that we know from the first chapter, but to revise again, it's a series where one previous number is added to the present number in order to obtain the third number. So this is the Fibonacci series code. As you can see, this is the declaration, it's being called, and this is the definition. So let's say that we want a Fibonacci series of 3 numbers or so. So in that case, n value is 3. So as you can see, the integers n1, n2 and n3 are declared as static in the function definition. So the reason behind this is that in order to obtain the Fibonacci series, it's important to remember the previous elements. So after each iteration, it remembers the previous iteration's values and it does not begin as a fresh new iteration. So let's start for 3 number of elements of Fibonacci series. So as you can see, the first element is 0, second element is 1. So the third element to check is third element is equal to the sum of the first 2 numbers. That's 0 plus 1, and that's 1. So that is executed over here. We get the third number as 1. then n1 becomes n2 and n2 becomes n3. So what happens is that the first element is no longer 0, it becomes 1. And the second element is again 1 because that is equal to n3. Now the function is again being called and repeats and goes to the function definition until n is greater than 0. Let's execute this. Let's obtain for, let's say, 5 Fibonacci elements. So as you can see, 0, 1, 1, 2 and 3. So 1 plus 2 is coming out as 3 and 1 plus 1 is coming out as 2. So the last and the most important program for the recursion is the Ackermann function. It's also one of the best examples for recursive functions. So how is an Ackermann function defined? It's defined by these 3 conditions. So we input 2 numbers m and n, and these 3 conditions are checked. So let's get a better understanding of this while executing the function, the entire program. So as you can see, this is the Ackermann functions program. The function is being declared and it's also being called in the printf statement. So we input 2 numbers m and n, and this is the function definition. So let's understand this while using an example. So let's take, we input 2 numbers which is 1, 1. So m and n both values are 1. So let's check the function definition and we'll execute this program with our own logic. So first we check, is m equal to 0? No. Is m greater than 0? Yes. But is n equal to 0? No, because it's 1, 1. So then we go to the next condition, which is m greater than 0 and n greater than 0. That is true because we took 1, 1 and both of them are greater than 0. So we get the return value is an Ackermann function again because it's being called, and that has an m value of m minus 1. But in this parameter, it's another Ackermann function where it is m, n minus 1. So we took the example of 1, 1. So this will become a of 0, and Ackermann function here will become a of 1, 0. So in the next iteration, it tries to solve this part of the Ackermann function. So it goes, let's go back to this definition and again execute only this part of the Ackermann function. So here, as we know, the value of m is 1 and this part is 0. So let's check the conditions. So first we'll check if m is equals to 0. That is not true. Then we go to check if m is greater than 0. That is true. And is n equals to 0? That's also true. So in that case, we return this function value. So in this case, it will become a of 0, 1 because m is 1, that we know, and n value that part will become 1. So now this is again called and it's executed over here. So as we know, it's a of 0, 1. Here the first condition is met because m is 0. So n value, which was 1, becomes 1 plus 1, 2. So this entire value of this Ackermann function is 2. Now we'll execute this whole part again. This is again called to the definition. So it's a of 0, 2, right? So in this m is 0. So since the value of n here is 2, it will become 2 plus 1. And the final value is 3. So the output will be 3. So let's execute this and check. So enter 2 numbers 1, 1. And the output is 3.